Single server queuing model. So single server queuing model, the Kendall's notation for this single server queuing model is M1. So Python arrivals assumptions of single server queuing model. First one is Python arrivals. Arrival rate follows Python distribution. Second one is negative exponential departures. Negative exponential departures. Third one is single server. We are assuming only one server is there in the system. Priority rule is first come first serve. Priority, if he has not mentioned any priority rule, means first come first serve or first in first out. He has not mentioned in Kendall's notation system capacity also. So then system capacity is infinite. And another thing assumption is always service rate is greater than arrival rate. Then only queue forms. Service rate is represented by mu greater than arrival rate. So queue will form only when this condition is satisfied. Arrival rate is number of customers coming arrived per unit time. Number of customers arrived per by time taken. This follows Poisson distribution. Departure rate. Number of customers left the system or departure divided by time taken. So here the traffic intensity, how is the system utilization, is defined by the system utilization or busy period, how busy is the server, or traffic intensity, what is the traffic, is defined by rho. Rho equal to lambda by mu. If this value, so this rho value lies between 0 and 1. 1 is 100% utilization, 0 is there is no one in the system. Okay, so few other characteristics, operating characteristics are probability that no customer in the system, probability that there is no customer in the system is given by P naught is equal to 1 minus rho 1 minus lambda by mu. Similarly, probability that there are n customers in the system equal to Pn defined by Pn, then 1 minus rho power n. System and queue, how you have to understand the difference between the what is system and what is queue. Suppose there are 3 people in the queue and one person is taking service with server. So total combined who are in queue and which are another person who is taking service is called system. The people who are in queue is called only waiting. So this is the difference between the queue and system. So based on this, average length or expected number of units in queue. Average length of single server queuing system. Average length of queue or expected number of units in queue. Number of units, number of people, everything in queue equal to length of the queue. It is also called LQ. LQ equal to lambda square by mu into mu minus lambda. So the derivation basically not required, that's why I am giving formula for the length of the queue. Because of time constraint, we are not going each and every detail of how is the derivation. Anyway, for gate purpose you don't need to know the derivation for all. Similarly, average length of the average waiting time or expected time in queue. Average waiting time in queue is equal to WQ equal to lambda by mu into mu minus lambda. It is also can be written as LQ by lambda. So next one is average length of system is equal to LS equal to LQ plus units served, as I showed in diagram. So LS equal to LQ, we know that lambda square by mu into mu minus lambda. Unit served in the system is shown as lambda by mu. After simplifying, the value you will get is lambda square by mu into mu minus lambda. So simplification, actually this is not the right one. So lambda by mu minus lambda, there is no lambda square here. Lambda by mu minus lambda. Average time in system. Average time spent in system is equal to Ws is equal to 1 by mu minus lambda. It can be written as Ls by lambda. System utilization, we have already discussed rho, and expected number of units in queue for busy system. Expected number of units in queue for busy system is equal to LB, nothing but L lambda by mu minus lambda. Expected time in queue for busy system. Expected time in queue for busy system is nothing but WB equal to 1 by mu minus lambda. Is also called average waiting time in non-empty queue. It's also called as average waiting time in non-empty queue. Next is probability density function for time spent in the system, or variance of number of units in the system. These are all derived from this. So probability that the queue size is greater than n. Probability that queue size is greater than or equal to n. So P of q size greater than or equal to n is equal to lambda by mu whole power n. So probability that the q size greater than n is denoted by lambda by mu whole power n plus 1. Probability waiting time in queue is greater than w equal to w is similarly probability that waiting time is greater than or equal to W. In system, waiting time in system greater than or equal to W is equal to W to infinity mu minus lambda e power minus mu minus lambda W dW. Same way, probability waiting time in queue instead of system queue, it is greater than or equal to W. It is written as W to infinity lambda into 1 minus lambda by mu e power minus mu minus lambda W dW. Little's law. Little's theorem or lemma law is a relation between length average number of customers in store L equal to lambda into W. L equal to average number of customers in store. Lambda is arrival rate. W is average time a customer spends in store. Average time customer spends in store. GATE 2010. Question number 1 in page number 43. Question number 1 page number 43 in GATE material. GATE 2010 1 mark question. So Little's law is relationship between Little's law is relationship between options are stock level and lead time in an inventory system. No. Option B is waiting time and length of queue in a system. Yes. Option C, number of machines and job due dates in the scheduling problem. No, it's not scheduling problem. D, uncertainty in the activity time and project completion time. So D also not. So answer is C. Little's law is a relationship between waiting time and length of the queue in the system. Waiting time and length of queue in the system. Question number 10 page number 105 GATE 2008 question. So in a MM1 queuing system, MM1 means M/M/1 means single server queuing system. We have in syllabus only single server queuing system, so we need to study only that. The number of arrivals in an interval of length t is a Poisson variable, that is probability of there is being n arrivals in the system t is e power minus lambda t into lambda of t whole power n by n factorial. The probability density function ft of inter-arrival time is given by. So he has given exponential Poisson distribution. He is asking inter-arrival time distribution. Probability density function of inter-arrival time. So we have already written about inter-arrival time. We have discussed that inter-arrival time follows negative exponential distribution. So the A he has given is lambda square e power minus lambda square t. B lambda e power lambda t minus lambda t. Sorry, that is lambda C. B is e power minus lambda square t by lambda square. D e power minus lambda t by lambda. So out of all options, C is the answer. We have already discussed the exponential distribution formula. So C is the answer. C is lambda power e power minus lambda t. Next question. Question number 21. Page number 107. Gate 2005. 2 marks question. Consider a single server queuing model where Poisson arrival rate. So arrival rate is equal to 4 per hour. Exponential service rate. Service rate is 4 again, mu equal to 4 per hour. The number in the system is restricted maximum to 10. The probability that a person who comes and leaves without joining the queue. This is special case problem. That's why they asked this. No, because here mu equal to lambda. Whenever mu equal to lambda, then probability that when mu equal to lambda, generally mu has greater than lambda. Whenever mu equal to lambda, number of customers in the system, the probability that the person who comes and leaves without joining, so Pn equal to 1 by n plus 1. Here P10 is equal to 1 by 10 plus 1 is equal to 1 by 11. Answer. So A is the answer.